Yesterday I gave a pretty general tutorial on sparse coding, and now we're going to talk about a kind of very specific thing. I complained about the why yesterday, and I'm going to be part of the problem now and continue working on the how, even though the why is, even the if we should is not clear. I'm going to talk about the how anyway. So, okay, so yesterday we saw a couple of dictionary learning problems, or several dictionary learning problems, and one of them was this guy here. So this is the basis pursuit, or the relaxed dictionary learning problem. And we wanted to train a dictionary and some coefficients so that they, together, the product of the dictionary and the coefficients matches the data that we have as well as possible, with a penalty on the sparsity of the coefficients. The problem is when you go at test time to compute new coefficients, you have to run an optimization for every data point, which can be annoying and slow. And so if for example, the data is very if the coefficients that you want, if the regularization is very strong and the things are actually very sparse, maybe you can do stuff about as fast as multiplying w times x. But if it's less sparse, you may have to do many iterations of ISTA or FISTA or something, and you don't want to do that. So the first idea we'll talk about is really nice, and it has a lot more implication than just what to do for sparse coding, but it's to train an encoder with the dictionary. So instead of training this thing here, where you train the dictionary and the coefficients so that they match the data, you train the dictionary and the coefficients so they match the data, and so that the coefficients are sparse, but so that the coefficients are easily approximated by some parametric function that you control and is easy to apply. So you add one extra term into the thing. You say, I want to make this not only a sparse approximation which has good reconstruction error, but I want it to be a sparse approximation which has good reconstruction error and is easy to approximate by this function, f theta. And theta will just be f theta is some parameterized function, and theta are the parameters. So the first place where I've seen this sort of thing is in a paper of Kurai Cavacolo, Marco Aurelio Ranzato, and Jan. And there f is taken to be a one-layer neural network. It's just a 10H with some a bias and weights and some gain parameters. You might imagine that you could do more sophisticated things, and we'll talk about some of the more sophisticated things. So the simplest, more sophisticated thing you might imagine is, instead of a one-layer neural network, you do a multi-layer neural network. And this is actually extremely natural. So we mentioned this briefly in the last lecture, but we'll say it again here. So in Carl Greger and Jan LeCun's paper, they train a multi-layer neural network to regress the sparse codes in the same sort of way. Let's look at why this is exceptionally natural. So here I've written up a slide from the last talk. It's ISTA. So by now you guys have seen this at least 3 times, because you saw it in Stephen Wright's talk and yesterday and now again today. So here's ISTA. Again, this is proximal gradient descent. You take a gradient step, and then you have a proximal step. So you take a gradient step with respect to the smooth part, and you take you try and minimize the non-smooth part while staying close to the gradient step you just made. That's this guy here. And then you repeat a while. So this is ISTA. If you rewrite ISTA with the correct variables, and they really are the correct variables, because if you want to code it, it's actually nicer and faster this way. You pre-compute the covariance matrix, and you compute B, just the product of W times X once, matrix times the dictionary once. And you let the matrix A be I minus eta Q. So what does ISTA look like? I don't know what this T1 is doing here now, so ignore it. So you initialize z equals 0, and then you just keep iterating these things, these steps. Az minus B, shrink eta lambda. So
I don't see X on the right-hand
Sorry, this is completely screwed up, that's why. Sorry, this should be a zk plus 1, and that should be a zk. This slide is just, this slide is goofy. I have no idea why there's a t here either. So again, this should be a zk plus 1. This should be a zk. So each iteration is just applying a to zk. You subtract off the bias, you shrink by eta lambda. And that's the iterations of ISTA. So again, zk plus 1 here, zk here. Sorry for that. But what you can see is this is just, if you do k ISTA iterations, then you have a k-layer neural network with shrinkage as your nonlinearity, right?
Looks like a recurrent.
It is, in fact, a recurrent neural network. But it doesn't have to be. You don't have to use the same A at every step if you didn't want to. So the way it's written here, it is, in fact, a recurrent neural network. So these guys trained A. And actually, Carol played with training this guy here as well. But training A's and B's is the thing that really worked well. And it actually does work. It actually does improve the convergence speed of FISTA, especially when you know you're only going to have a few iterations. So if you say, yes?
So you train A without the low rank constraint?
There's no rank constraint on A.
But there is almost, right? It's the decomposition into a diagonal plus low rank.
Okay, so let me say a couple things about that, because it's a good idea that is not actually necessary. So it's worth talking about. So right now, W is an overcomplete dictionary. So Q is actually not low rank, because W is huge. W is D by K, and remember, W is usually overcomplete, so K is huge, and so this is more than rank. But actually, if you want to kind of do this fast, you might want to choose. If you want to do this really fast, you might want to be able to multiply A times Z, right? Fast, and there's lots of constraints that you could make on Q, or that you could make on A when you're training this, so that you can actually do this even faster than fast. For example, if A were FFT, you'd be really happy, because each multiplication would be just a column operation, essentially. Would be an n log n operation. But right now, there's no, as it is now, Q is a full rank matrix. Okay, so this gives a nice speed up. There is a different version that they have for coordinate descent that also works really well. And actually, I left up the ISTA one because I showed the ISTA slide before, but the coordinate descent one looks really nice. If you do, for each of the algorithms we talked about yesterday, I discussed that you can write it in the compact form, storing the covariance matrix, storing the Gram matrix, and keeping everything in the Z space. If you look at coordinate descent, when you've done this, it actually has a very nice form. It's very, you just take max, there's just max operations, and you subtract off rows of Q from the current iterate. So every operation is a column operation. And you can do the same thing. You can do the same thing for coordinate descent, and it works well. But there's something cool here, and it's actually, I'm not going to talk about it anymore in this talk, but it's, I mean, for people who are just starting research, I think it's just a tremendously important thing that is essentially unexplored, which is the general idea here goes way beyond sparse coding. It's what you're doing is you have an optimization problem that you're going to have to do lots and lots of times, because you're going to train this thing, and then at test time, someone's going to give you lots of test examples, and you want to be able to do it very fast. But your test examples come from a certain distribution. So what you're doing is you're trading a general purpose optimizer for an optimizer that might fail on data that you don't care about, but it runs faster on data that you care about. So having an optimizer that's trainable is really cool. It means, and I don't think it's very studied. It's a really kind of open area. So not just in sparse coding, in everything, in like computer graphics, and in modeling of PDEs, and just a million different places. There's room for having optimizers that are special for the data that you have. Yes?
In your PSD slide, did you actually write the data update for your?
No, no, I didn't write it. But
so what is the data update?
Well, for the PSD, for the single layer one, it's actually, I mean, it's pretty. You can just write the derivatives. It's pretty easy, right? You don't even have to do backprop, right? It's just there's a single derivative, and it'll look like the other. The one in this one, you'll have to write backprop, but they're not that complicated. So look in Carol's paper is the simplest answer. But for the single layer one, it's just going to be each of the matrices transposed against the. Okay, so that's really cool, and these are really good ideas. But all these methods require multiplying the dictionary by the data, and there are actually times where you don't have time to multiply the dictionary by the data. Your dictionary is large, you have lots of data, you can't even afford one multiplication. So how can we get past this? Well, one thing that seems really promising is to have tree-structured dictionaries. If your dictionary was structured like a tree, that would be really nice because maybe that structure would help you to do the coding very fast. So one way of doing this is we talked about this briefly last time, but one way to do this is to say, well, we want to have a sparsity dependency on the branches of the tree rather than on the individual code elements. So you don't pay when you turn on a code word, well, you might pay for that too, but you pay every time you turn on a branch of the tree. So let me show you what I mean. So what you have, the equations are written up there, but I'm just going to look at the picture. I'll just talk about it in the picture. What you have is a group. This is all the dictionary elements. Then you have another group, which is this whole branch here. Then you have a group which is this branch, and this branch. And if this were a bigger tree that fell off the thing, you'd have, for every branch of the tree, you'd have a group of elements. Now what you pay for is turning a group on. In other words, if this guy turns on, then you pay. And there are lots of ways of writing this. This is one of them. But usually what you end up with is a mixed norm. So here you have the normal L2 error on the reconstruction term, but your regularization term on Z makes you pay. If you turn on this one, then you kind of pay for that whole block. If you turn on this one, then you pay for this whole block, this block, and the whole thing. If you turn on this one, you do this. If you turn on this, you only pay once. You only pay for this, but you don't pay here, here, and here. So this was studied by, I think this is the first place where this model appeared. There's a different model where this is kind of intersections of groups. There's another thing by Francis Bach's group where they have union of groups, and actually Julian Morel and Francis Bach group has really nice algorithms for doing these things pretty fast. And that's cool, but the thing is, it's not actually faster than doing the original basis pursuit problem, at least when you formulate it in this way. You get really nice results. I guess I should have put the picture. For example, if you train this on image patches, you get the root of the tree is just the DC component, and then as you go down the branches, you get sharper and sharper edges. It really kind of fits with what you would want to happen. But it's not actually faster than doing the basis pursuit, and a lot of times it's slower, depending on the exact formulation that you use. So you could try something else. You could try to be greedy about it and say, well, I'm going to train my dictionary in this tree structure, and just if I'll walk down the tree, and if I turn this guy on, then okay, I can continue down the tree, and if I don't turn it on, then I'm not allowed to look at any of his children, and I won't turn any of those guys on. The problem is that really doesn't work very well. I've seen several papers that try it, but my experience has been that simply fails. It doesn't do any of the things you want it to do. So, okay, that's too bad. But we still want to kind of not give up on this tree idea. By the way, I'm leaving out a lot of things here. This one has to do with trees. This is a completely different way of thinking about speeding it up that actually I'll talk about again. I'm saying I'm leaving it out, but I'll bring it up probably again. So this is going to be talking about nearest neighbors, using the nearest dictionary elements instead of a tree. But so we don't want to exactly give up the tree idea. So a different take on the tree idea, instead of having a dictionary which is structured by a tree, which you'll still get, but we're going to explicitly partition the data into a tree. The idea being that when a new point comes into code, we can kind of find where it belongs in the data. And then, based on that kind of multi-scale partitioning, decide what the coefficients ought to be. So this is the idea of the geometric wavelet transform of Allard, Chen, and Mangione. And so again, what you do is you have your big pile of training data. and you take as the root of the tree the principal component of all of the data. You take the best linear fit to the data. Then you have this partition that you've built some other way. So for example, in their paper they use METIS, which is a graph partitioning algorithm, or they use cover trees. But you have this partition, and you say, okay, let's go to the next level of the partition. You have however many pieces that the partition gave you. And on each piece, you remember the difference from that part of the data to the whole data. So you calculate the principal components of that small part of the data, but you project onto the orthogonal complement of that principal component of all the data, right? And then you repeat on the finer subdivision, and you repeat on the finer subdivision, and so on and so forth. What you get is what they call a wavelet transform of the data. And by the way, I've mentioned this one paper, Chen Magioni. Actually, this in harmonic analysis is quite an old idea, and at least 1980, and I'm sure much earlier. But the idea that you can take a set of data and apply a multi-scale wavelet type transform to a set of data is actually very, very old. But this is the first place I've seen it coded in that way. So, but mathematically, it's a reasonably old idea. And it's actually very powerful. It's mathematically a very powerful idea. So this actually is a cool paper because the way they do it, they kind of have algorithms for estimating the dimension of each piece and deciding how many principal components are at each layer. And they actually have provable approximations. So this is one of the few sparse coding papers I've seen that in a geometric way has kind of provable theorems about when it will work. But again, classical manifolds are not something you really usually see in data analysis. But okay, so this is actually getting kind of getting pretty cool because if you can actually follow a point down the partition, then you should have a pretty fast algorithm. But the truth is, if you look at the code, it's not yet working yet. So you can't. The way they partition the data, it's hard to actually get this fast. Theoretically, it works, but they use partitions that aren't easy. And then there's something else, which is slightly annoying. It's not obvious that the tree that you use to partition your data needs to match the tree of the dictionary structure. There's no reason for those two things to be the same. One thing is an encoder. The other thing is the thing that you actually want to get. So the question is, can you do anything else? And so it turns out you can. It turns out that the thing that you're using, the partition doesn't need to have anything to do with the dictionary. You can just use a nearest neighbor type hash as an encoder. That's the long story. That's a short version of the story. So what do we want? We want, given an input x, we want to be able to find the active set of non-zeros in Z really fast. And by really fast, I mean that you don't get to ever multiply W times Z. That takes too long. So in some sense, this shouldn't be so surprising that something like this might work, because if you think about very sparse coding, if you want to do sparse coding where just a constant number of things, like 5, are turned on, it's almost like nearest neighbors. It's similar in feel to nearest neighbors. It's not exactly the same, but it's similar in feel. And there again, I want to point out this paper of Caillou's group, where they actually explicitly use nearest neighbors they use the nearest dictionary points as their coding. But the point is that you shouldn't, in some sense, be surprised that you can get some sort of hashing type solution, some sort of approximate nearest neighbor type solution to the sparse coding problem. So what you want is a hashing function, some function that you input your x and it outputs some finite number of values, and that finite number of values shouldn't be too large. And then you're just going to associate to each of the L active sets, each of the L hash buckets, you're going to associate active set. You're going to associate a list of possible things that can be turned on at that active set. So when you train this thing, when you kind of build this up, you're going to cache the active sets and say the pseudo inverses of W there, and at runtime everything is very fast because you've kind of memorized everything. And of course you need to learn everything. That should have gone on the previous thing, but I guess it fell off. So of course you need to learn everything so that this works. Okay, so I'll give an example where you use a binary two-means tree or KD trees as your hash functions. I guess this isn't the normal way people say hash when they're talking about nearest neighbors. Usually they mean a linear hash and then a thresholding. But here we'll just say we build a tree on the data, and then given a new x, we follow it down the tree. And we've memorized the active set at the leaf where x ends up. And so now actually doing the dictionary coding is very fast because you only have to multiply by those few dictionary elements, or even better, just by the pseudo-inverse that you've cached. So there is some of this. It's not uncommon when you want to speed something up that you pay by remembering stuff. And here, depending on how much you remember, you can actually have quite a big data structure. But if you want to remember less, for example, if you don't remember pseudo-inverses, actually the data structures aren't that big. It's just the hashing functions. And remember, the problem that you're solving here is easier in some sense than nearest neighbors. You don't have to remember the entire training data set. You just have to remember which W's, which columns of the dictionary were being used at that point. So what does it look like at test time? Someone gives you your x. Let's suppose we've trained a 5-element dictionary. And we've trained the tree, and we've remembered the active sets for the different, so here are the leaf nodes in the tree. And so someone gives us the x, and we've remembered the pseudo-inverses of W on each of these things. And this is, right now I'm talking for the L0 coding problem. Then we just pass x down the tree. So x gets sent down the tree. It got sent to A1. So now we just have to multiply x times the pseudo-inverse that we've remembered for that node. So it would be better if you could use linear hashes instead of trees. There are lots of reasons why, but the simplest reason why is because of this. Linear hashes interact really nicely with OMP, with every kind of sparse coding algorithm where you can play this covariance memorization game. In other words, all the algorithms I talked about yesterday have the property that you can store the covariance and just do column updates or do some compressed updates once you've stored some things. And actually, if you could use a linear hash, if you could do the whole thing in the low-dimensional linear binary space, sorry, the low-dimensional binary space given after you multiply by the linear map, you can use all these things there, and everything can be done kind of on the binary space, and you can update that as you add each element or as you do each ISTA update. And if you could do that, you could build a fully convolutional version of this that would run really fast, much faster than the actual convolution. So if somebody wanted to run a convolutional net with thousands of filters, you could do it, as long as you know that only a few are on at each location. Unfortunately, it's not trivial to make. For whatever reason, linear hashes don't give you very good accuracy. So whatever. Okay, so let me kind of talk about how you might train everything together. There are lots of ways to do it. Let's assume that the hash is fixed. Again, we used either binary two-means trees or KD trees. And you can train the dictionary to match your hash. In other words, we want to make this whole encoder scheme work. We want to train the dictionary along with the list of active sets, along with the dictionary and the list of active sets together, so that the residual is as small as possible. So here we used a batch algorithm. You associate to each hash bucket, you associate the best active set for that. For the first step, for this step, you use some sort of simultaneous coding. In other words, when you measure the error, doesn't matter which. When you measure this error here, when you measure the residual error, you don't do it on each x, you measure that error on all the data points in that hash bucket. I should have written, there should be a reference here to, there should be two references here actually. So a paper of Julian Morel on image noising and a second paper of Guillermo Shapiro's group on hierarchical sparse coding, where they actually do something very similar to here. So then once you have the active set that's associated to each leaf of the tree, then it's easy to update the dictionary elements. You just use KSVD or whatever you want, gradient descent, it doesn't matter. So let me show you how much of an improvement you can make on a simple case. Dictionary learning is a subset of near subspace. In, say, L0 dictionary learning, if you have k atoms and q non-zeros, you have k choose q subspaces. Right? It's a lot of subspaces, but it is, again, it's just a near subspace problem. So here we're going to just pick 240 10-dimensional subspaces. We train them using the k-subspaces algorithm. And it's trained on a million CIF vectors. We'll talk about CIF vectors in a little bit, actually, if you don't know what they are. But just think this is some data. You have a million data points, and you train a model with 240 subspaces. And now, for each point, at test time, you have to find which is the near subspace to you. That's the same as finding active set in the dictionary. And what you find is that, so this axis here is the number of comparisons you have to make. This axis here is the residual energy. The green is when you find the best possible subspace. This is the exhaustive search. And what you find is, after just a few comparisons, so you run your hash and you remember at the bottom, at the leaves of your hash, you remember what the most likely near subspaces are. You say, okay, I'm going to remember those, and I just go through in order of likelihood, and I stop after a fixed number. And after very few comparisons against subspaces, you get to essentially the optimal energy. So this is the total energy, total average energy. This is the average energy of the best fit subspace. This is after after m comparisons. So here m is like 5, and here m is like 10. So the number 240 there doesn't matter. If you do 2,400, you get the same picture, actually. It doesn't change at all. And the fact that I'm doing near subspace search with completely unrelated subspaces doesn't matter either. If you do this with, say, subspaces that came, for example, if you use a tree structure dictionary and the subspaces are just the branches of the tree, the same thing happens. If you do, for example, a grid, what they call, a grid structured dictionary, the same thing happens. Yes?
Is this 240 choose 10 that you're talking
No, literally just 240. It's just, I did k subspaces with 240 different 10-dimensional subspaces. So it's a dictionary.
How did you choose these 240?
K subspaces. So you train it. It's if you want to think about it this way, it's a block 1 sparse dictionary with 2,400 elements. So okay, so let me make this clear. So you have 240 10. It's just k-means. 2,400. But that's not the right way. It's just you run k-means, but instead of having a center, instead of having one center for each cluster, you have a subspace for each cluster. So it's 240 means, except you have a subspace for each cluster. If it's not clear, you can think of it as a Gaussian mixture model with 240 mixtures. And actually, the same thing works here. If you just, instead of energy, you put likelihood here, and the same thing happens if you do a Gaussian mixture model.
So 240 is the size of the tree.
No, the tree is huge here. The tree has 64,000 leaves. It's a 2 to the 16 tree. So again, the whole point here is to get the tree, which you use as a hash, to be, it's just the encoder. It's independent of the structure of the dictionary. The thing that's interesting is this works independent of the structure of the dictionary as long as the dictionary is reasonably well structured. So again, here we just have 240 subspaces, which are trained like k-means. It's just k subspaces. And they have nothing to do with the tree in this case. Now I train a new dictionary which does care about the tree, which respects the hash and all that. And this is how I do that's how I do the coding to get the blue line. And the point is, it wouldn't have mattered if I did k subspaces or a tree type dictionary or any other structured dictionary. You would get really good residual.
So what about a usual dictionary?
Just pure dictionary. Okay, so then what happens is you get a line that looks like this. And the problem is, by the time you get to here, the amount of time it took you to run the hash and do that many comparisons is more than actually it took you to do the OMP, for example. So, but this is going to be actually important for the next part of the talk. So if I try and actually approximate an OMP with this sort of scheme, then it doesn't work well in terms of reconstruction error, but it works well in a different sense. So we'll say what sense it works well. So for structured dictionary, we have a very strong, at least empirically, very strong sense in which it works. It does as good in the energy that you were trying to measure as the original thing, much faster. If you try and do an unstructured dictionary, hashing like this fails in terms of reconstruction error. However, let me skip this because I want to get through. However, in the context of a pretty standard object recognition system, it works just as well. And what that will call into question is, what is the sparse coding doing? Because you can check that the reconstruction error is completely not like what you're getting with the actual sparse coding, but so you're getting completely different responses, but somehow it still works in that setting. So, okay, so let's talk about the object recognition system, because it's interesting by itself. In some sense, so I wasn't here for Hinton's talk, but I've heard about it, and almost I don't even want to talk about this because that's really impressive what he's doing. But I'll talk about it anyway because it's always good to have not a monoculture. So we'll talk about the Sift pyramid system, which for a while was actually as good as you could do. So how does Sift pyramid work? So Sift pyramid is actually very similar to convolutional nets in a lot of ways. It's just different parts of it aren't trained. So it's a multi-level system that has, as its first layer, dense Sift. Its second layer is sparse coding of Sift features, and there's lots of choices of exactly which sparse coding you use. There's probably 20 papers on this, and one of the main differences between each of the 20 papers is which sparse coding they use in the second layer. And the third layer is a linear classifier, and there's pooling in between. So the only thing that is trained here is the coding and the classifier. The coding is trained unsupervised, the classifier is trained supervised. So this is, like I said, the same kind of system as a convolutional net. If you step back far enough, each layer of this system is normalization, filter array, coding, pooling. So the first layer of the system is Sift. So Sift is a really popular low-level image descriptor, if you guys haven't seen it. And it was originally used for image matching. In other words, you want to find, like Tiny Eye, you want to find an image that's exactly the same as your image somewhere. Or you want to do you want to find stitching. You want to find a place in that image that's exactly the same as this image. More recently, people said, oh, it's also a good feature for object recognition. So how does Sift work? You input a grayscale image, and the normalization, there was a brown box there. The brown box is empty. You don't actually normalize the image. You filter the image with an approximation to the gradient. You code it by soft k-means. So there's 8 essentially angular bins. It's essentially a soft k-means for the second step with some very carefully engineered parameters that are super important. It's the only time I've ever seen the L9 norm. But anyway, so it's basically a soft k-means here, and then there's a pooling step because you average into 4x4 blocks. And there's actually one more step for Sift to make it into Sift, which is some sort of normalization. But I'm going to skip. I'm not going to put that in this block because if you put it into the kind of that convolutional network architecture, really that belongs in the next layer. So after you filter, code, and pool, after you filter, code, and pool, you normalize over 4x4 neighborhoods of the image. So the whole SIFT pyramid system is you filter, code, again, soft k-means, you do a pooling, then for the normalization, it's basically a 4x4 divisive contrast normalization. Then you have a filtering with k sparse coding words. So again, the first layer is SIFT, the second layer is sparse coding, and the sparse coding is filtering and then some sparsification. And then you max pool into a spatial grid, and that's the pyramid. The word pyramid comes from this final stage where you pool in over the whole image the codes that you get, and then maybe 2x2 blocks, and then maybe 4x4 blocks. All in all, the system really is very much like a convolutional net. It's just you only train this part unsupervised, you train this part unsupervised, and this part is engineered. And actually, the normalization here is engineered. For a while, this did quite well. To make it work, you actually need a very large dictionary size. So the dictionary has to be really large, and you have to take SIFT vectors at every location in the image. And actually, you can't do sparse coding if you want to run this in real time. And in fact, you can't even multiply the dictionary times the data. You have 15,000 SIFT vectors on your 240 by 320 image. Each one is 128 dimensional. Your dictionary, your K is like 4,096. So you have a 4,096 by 128 matrix to multiply against a 128 by 15,000 matrix. That takes you already like 0.4 seconds on cores. So you can't even multiply the dictionary by the data. So you have to use something like what we talked about earlier. You have to use an encoder that doesn't force you to multiply the dictionary by the data. So we implemented this SIFT pyramid system, and we have a fast SIFT descriptor. Actually, there is a better fast SIFT descriptor than the one we have, but I didn't realize that until too late. So Andrea Veldaldi has the VLFeet package, and they actually have a really nice fast SIFT descriptor in it. But anyway, so when all is said and done, the full machine gets 30 frames per second on a 4-core machine. So you can run it in real time. And you don't lose any accuracy compared to using regular sparse coding on Caltech 101, Caltech 256, and scenes. So let me just show the tables. So if you run a full sparse coding, so this is good SIF features, like slow, good, careful SIF features, and full sparse coding. You get, with a big dictionary, you get like 75%. This was near state of the art with single features a while back. It's now a little bit behind, but we're doing the most vanilla version of this system. If you use the fast hash sparse coding with the system, you only lose about 1%. And actually, you can get the same thing back by just doubling the size of the dictionary. And of course, with the hash sparse coding, it doesn't matter if you double the size of the dictionary. It costs the same amount of time to get the code. If you do the sparse SIFT and everything together, the fast SIFT, you lose a little bit more accuracy. But I just want to point out that using the fast coding costs you almost nothing in accuracy. On the other hand, you get stuck with the question because the coding was really, really crappy. Like when you asked, what happens when you use OMP? So here was an attempt to approximate OMP. If you look at the L2 error, it's much worse than OMP. It's almost 2 times the error for the same size dictionary and same number of non-zeros. But you're only losing 1% in accuracy, which is saying that whatever sparse coding is doing in this system, the reconstruction accuracy actually doesn't matter that much. And this has been seen over and over and over and over again. So for example, again, I'm going to talk about this Caillou paper. This Caillou paper, this paper of Caillou's group, there's many other authors, that use the local coordinate coding that use you just take the nearest neighbors to your dictionary and code that way. This one, again, if you look at the reconstruction accuracy, it's terrible. It's not very good at all. But it does quite well in terms of accuracy within the system. And there's lots of other kind of dictionary learning algorithms that have the same thing. They don't actually give you very accurate representations, but they give you very good object recognition performance. So it is not clear at all what it is that you have to do at the coding stage to make it work. By the way, it is very important that you use some sort of sparsity. If you just try and do I'll qualify that in a moment. If you just try and multiply by your dictionary, then it will fail. And in fact, if you kind of play around with manipulating the sparsity parameter, you see that if you're going to do dictionary learning, as you make it less and less sparse, your error goes higher and higher. So it actually does, the sparsity does actually affect the system, but being accurate in your sparse coding doesn't affect the system. You just have to get something that's sparse. And so it would be really good to have some idea of what to do here. Again, there's a reference that should be here, which is Elon Burrows' paper in CVPR of 2010, where there are some principled methods for determining the sparsity, but really it's not really well understood. It's not really well understood what kind of dictionary you should have. And so the question is, does sparsity even matter? And actually, right now, the current winner, the current best version of this system is some people at Xerox. So it's Peronin and Sanchez and Cordelia Schmidt, and I can't remember the other authors, but their system uses something called Fisher vectors. And there is some sort of nonlinearity. So you code against, it actually looks very similar to sparse coding, but the actual vector they get isn't sparse. They code some variances and differences from means against a bunch of Gaussian mixture components. And that's currently, as far as I know, the kind of best version of this system, and there's no sparsity. There is the nonlinearity of looking at the different kind of blocks of code. So, so in the first lecture, I started off by saying, why do we use sparsity? And the reasons why were because it works. But actually, it's not clear exactly that it works or if you can take it away. And it's not clear what it is that's doing. So I'm a little bit ahead of schedule, but I'm actually going to stop, I think. And I want to end with saying, well, okay, so if it's, to the extent that it's working, we don't understand why at all. And I think a lot of the questions about the geometry that I talked about in the previous talk matter for that. But we also don't understand, when we use this in kind of learning structures, there's always pooling involved. And we don't understand the interaction very well with the pooling either. So I'll stop there.